My name is Reich and welcome to this week's episode of Quick Maths. Today we'll be talking about conic sections and their application in real life. So first of all, what even are conic sections? You probably took these things up in high school and forgot about them. So let me help refresh your memory. Conic sections are figures formed by the intersection of a plane and a right circular cone. Depending on the angle of the plane with respect to the cone, a conic section may be an ellipse, a parabola, or a hyperbola. In mathematics, an ellipse is a curve in a plane surrounding two focal points, such that the sum of the distances to the two focal points is consistent for every point on the curve. It has the following parts. The foci are two fixed points equidistant from the center of the ellipse. The vertices are the points on the ellipse that fall on the line containing the foci. The line segment or chord joining the vertices is the major axis. The midpoint of the major axis is the center. The axis perpendicular to the major axis is the minor axis. An ellipse is represented by the formula x minus 8 squared over a squared plus y minus k squared over b squared being equal to 1, where a squared and b squared are the square of the diameter of the shape of the along the x and y axes, and h and k represent the coordinates for the center of the ellipse. A parabola is a symmetrical open plane curve formed by the intersection of a cone with a plane parallel to its side. It has the following parts. It has a vertex. If the parabola opens up, the vertex represents the lowest point on the graph or the minimum value of the quadratic function. If the parabola opens down, the vertex represents the highest point on the graph or the maximum value. In either case, the vertex is a turning point on the graph. An axis of symmetry. Parabolas also have an axis of symmetry parallel to the y-axis. The axis of symmetry is a vertical line drawn through the vertex. A y-intercept. The y-intercept is the point at which the parabola crosses the y-axis, and x-intercepts or the points at which the parabola crosses the x-axis. A parabola is represented by the standard formula x minus h squared is equal to 4p times y minus k. A hyperbola is the pair of parabolas formed by the intersection of a plane with two equal cones on opposite sides of the same vertex. It has the following parts. A hyperbola consists of two curves, each with a vertex and the foci. The transverse axis is the axis that crosses through both vertices and foci, and the conjugate axis is perpendicular to it. A hyperbola also has asymptotes which cross in an x. The two branches of the hyperbola are on opposite sides of the asymptotes cross. The vertical and asymptotes can be used to form a rectangle, with the vertices at the centers of two opposite sides and the corners on the asymptotes. The center of the other two sides, also called the conjugate axis, are called the covertices. Where the asymptotes of the hyperbola cross is called the center. A hyperbola is represented by the standard formula x minus 8 squared over a squared minus y minus k squared over b squared is equal to 1. But outside of your mathematics textbooks, where else can you see these concepts in action? Surprisingly, you can find them in the real world. They appear in fields as different as architecture, astronomy, engineering, and even medicine. Don't believe me? Well, let's take a look. Examples of ellipses in real life can be found in architecture, astronomy, and medicine. In whispering galleries, a focus is one of 2 points that defines the shape and size of the ellipse. These are located on the long axis of the ellipse at equidistant points from the center of that axis. If light or a sound wave emanates from the one focus of a real-life ellipse, it will be reflected to the other focus. This property is used to create whispering galleries, which are structures that allow someone who is whispering in one area to be heard clearly by someone in another area, but not by anybody else. Famous examples of whispering galleries include the United States Statuary Capitol Hall and London's St. Paul Cathedral. Lithotripsy is a surgery-free method of destroying a kidney stone that uses the properties of the ellipse's two foci. For a lithotripsy treatment, the patient lies in an elliptical tub with the kidney stone aligned to one of the foci of the ellipses. Shock waves emanate from the other foci, concentrate on the kidney stone, reducing it to debris as small as sand, which can be passed through the body without discomfort. Because no incisions are made, recovery from this treatment method is relatively quick and easy, and in some cases, it can even be done as an outpatient procedure. Finally, the most common real-life example of an ellipse is in the orbiting path of a planet. Most orbits are not circular in nature, and they are often most similar to an oval or an ellipse in shape. Johannes Kepler's 3 laws of planetary motion are used to determine if objects have elliptical orbits. His laws focus on the elliptical orbits of the planets, and they allow the future position of the planets to be predicted, which is a great help to organizations such as NASA. Examples of parabolas which can be found in real life can be found in things such as engineering, physics, and even outer space. Consider a fountain. The water shot into the air by the fountain falls back in a parabolic path. It's similar to things such as balls thrown into the air, as demonstrated by Galileo, and anybody who's ever ridden a roller coaster before will be familiar with the rise and the fall created by the track as it parabolically arcs. Secondly, in things such as architecture, you can see parabolas. The Golden Gate Bridge in San Francisco, California is a great example of a structure which is supported by parabolas on each side of its towers. And if you want to go even further back in history, ancient Roman aqueducts and bridges also feature parabolas heavily in their design, as part of the supporting structure that helps keep these ancient bridges upright, some of which are still standing up to this day. Secondly, in things such as light focusing, parabolas are seen heavily. In lighthouses, using parabola-shaped reflectors helps focus light into beams which can be seen for long distances. You can see the same thing in headlights and even in solar power, because curved photovoltaic mirrors concentrate solar energy much more efficiently than flat photovoltaic systems. So the shape of these mirrors allows energy to be stored and made, which makes the process of getting solar energy much more efficient. Finally, in spaceflight, with organizations such as NASA, when rockets are launched into the air, they follow parabolic paths or trajectories, which have been used in spaceflight for decades. In fact, airplanes can create different gravitational environments by flying on parabolas, which has provided tremendous research for both human pilots and their spaceflight tolerance, as they have been able to simulate different gravities while still being in the Earth's atmosphere. Such flights save money by not only not needing to perform these experiments in space itself, but they're also kind of cool. Finally, you can also see hyperbolas in real life in fields such as engineering, physics, and once again, even in outer space. First of all, satellites. Satellite systems make heavy use of hyperbolas and hyperbolic functions. When satellites are launched into space, scientists use mathematical equations to predict their paths because of the gravity influences of objects in outer space. Using hyperbolas, astronomers can predict the paths of the satellites in order to make adjustments so that the satellites get to their destination. Second of all, in radio and navigation, these systems employ hyperbolic functions through trilateration, which pinpoints objects using its distances to certain points. So for example, in the cases of a ship, or another object needs to be located and the only things known are the differences between itself and two known points, The curve of possible locations is a hyperbola. These types of problems arise in navigation, but merely in nautical fields. So, for example, a ship can be located using the arrival time of signals from GPS transmitters, and this can be used to track people, cell phones, internet signals, and many other things. Finally, you can see this in architecture in hyperboloids, which are similar to hyperbolas, which are the design standard for all nuclear cooling towers and most coal-fired cooling powers in power plants. Because this design is structurally sound and can withstand high winds while still requiring very little material. For a given diameter and height of a tower and a given strength, the shape of the hyperboloid requires less material than any other form, and that's why engineers use it as the standard when creating these cooling towers. As we've been able to show you in this video, conic sections make appearances in many places outside the classroom environment, and are the basis for many of the things which we take for granted today and see in our everyday lives, such as the satellites which beam us up our internet, the energy generation plants which power our homes, the bridges that we cross every day, and the navigation systems which we use to guide us through the traffic as we go on through our day-to-day lives. Enjoy the video? For more videos like it, please don't forget to like, comment, and subscribe to Reich. Thanks for watching. Bye!